Okay, let's talk about the remainder theorem. The remainder theorem says you get yourself a polynomial. If you want to evaluate that polynomial at some value, another way you could do that is divide that by this linear factor, divide your polynomial by x minus k. Whatever remainder you get is the same as the function evaluated at that number. This is really handy for finding roots. Remember, a root is a place that makes the function 0. A value k, for example, that would make the function 0. So suppose I think 2 might be a root. I could just divide my function by x minus 2, see what remainder I get, and I would get the same value as if I plugged 2 into the function. And you're thinking, but why would I go through long division? Long division takes longer than just plugging a number in. Today, we're going to learn synthetic division, which can be much quicker. So it's a quick way to check for roots. It's a quick way to find function values. Okay, so we've got this function here. I want to evaluate it at x equals 2. So this is what we're trying to calculate. And maybe you should get your calculator out and actually evaluate what you would get here. And that will equal something. I'm going to calculate that using what's called synthetic division. So synthetic division is a quick way of doing long division. So I've got my dividend in here, the polynomial itself. Remember, if I were missing any powers of x, I would need to put them in as a 0 in here. If there were no x term there, I would need a 0x. And then outside, I'm going to divide by x minus 2. It's always x minus the thing you're interested in. And we could go through all this work, like you could try this on your own, but at the end, you're going to get some remainder. These are going to be the same number. But I'm going to do this long division using a shortcut called synthetic division. So what we do is we build this little box. We put this guy we're interested in outside, so 2, not negative 2. It's always x minus our number of interest here. Remember, that's who I was plugging in, was 2. Then I put all my coefficients here. Synthetic division is the same as long division. We just ignore all the x's. We just put in the coefficients. And again, if you're missing any powers of x, you got to remember to put in a 0. Okay, so we build this little box. And now what we're going to do at every step is multiply, add, multiply, add, multiply, add. So the first guy always just comes straight down, 6. Now at every step, I'm going to multiply and add. 2 times 6 is 6. Add straight down. -1 plus 6 is 5. 2 times 5 is 10. -15 plus 10 is -5. 2 times -5 is -10. Add straight down, we get 8. 2 times 8 is 16. 16 minus 7 is 9. Okay, so our final answer here, we normally box that off. That's a remainder. So if you were to do the long division, your remainder is going to be 9. Let me write that a little prettier. That also means that if you were to go through the math here, you can check this on your own, plug 2 into the function, you would have gotten 9. Now, we also figured out something else. This here will be the coefficients of our quotient up here. Remember, we're dividing a 4th degree polynomial by a 1st degree. So we're always going to go, when we're using synthetic division, we're always going to go down by 1 degree. So this is a cubic here. So these will be the coefficients starting with the third degree. 6x cubed plus 5x squared minus 5x plus 8. And then there's our remainder is the last one. So it's just a shortcut for doing long division. So we're learning two things here. Synthetic division is a shortcut for doing long division. Secondly, whatever remainder you get when you divide a polynomial by x minus k is the same thing you would get for plugging k into the function itself. Okay, let's look at another example. So I want to calculate f of -3. So that would be 2 times -3 to the fifth, and you see where this is going. And the answer is going to be -412. I've already done it here on a calculator. Which you can see here. I have plugged -3 into the function. We get -412. Okay, now let's get that same value using synthetic division. So I'm going to write up all of my coefficients here, keeping in mind that, see here, notice I'm missing an x. There's no x to the first power, so I'm going to have to put in a 0 when I get there. 8, 0, 2. The guy I'm interested in, -3 comes out here. Now, the first one comes down. Maybe I should leave a little more space there. First one just comes straight down. Then from now on, we multiply, add, multiply, add. -3 times 2 is -6. Adding straight down, -9. -3 times -9 is +27. Adding straight down, we get 18. -3 times 18 is -54. Adding straight down, we get -46. Multiplying -3 times -46 is 138. Adding straight down, we get 138. -3 times 138 is -414. Adding straight down, your very last number here will always be your remainder, -412. So again, we can use synthetic division to do two different things. To make long division much quicker. So if I were to take 2x to the fifth minus 3x to the fourth minus 9x cubed plus 8x squared plus 2. Oh, I need, if I'm going to do long division, I can't have any missing guys. I would have to have plus 0x plus 2. And then I'm dividing it by, it's always x minus the guy you're interested in. So minus a -3 would be +3. If I were to do this long division, here's what I'll get for my quotient, and I'm always going to have 1 degree less. So I started with a 5th degree polynomial. These will be the coefficients starting here at x to the 4th. 2x to the 4th minus 9x cubed, and you should try this on your own. 46x plus 138, and then plus a remainder. And remember, like in general, when you write out your remainder, you write it back over your divisor. That's also the same thing we get when we plug -3 into the function. So for some values, it's quicker just to plug it in. Like if I were trying to do x equals 1, it's just quicker just to plug 1 in. Like you can do that in your head. For other values, this is much quicker to see what we would get. Now, why are we going to be plugging a bunch of numbers into a function? Because we might be checking for roots. So here, we're going to use the remainder theorem to show that x equals 2 is a root of f of x is x to the fourth minus 16. Now, again, we could just plug in 2 to the fourth is 16 minus 16 is 0. I'm just doing a quick example here. So it's obviously a root, but I could use synthetic division. Now I've got a whole bunch of missing powers here. I've got a 1 for the fourth, no cubes, no squares, no x's to the first power, then minus 16. I put my 2 out front, draw my little line in. First guy always comes straight down, then multiply and add. 2 times 1 is 2. 0 plus 2, 2. 2 times 2 is 4. 0 plus 4, 4. 2 times 4, 8. Add down. Multiply. Add down. What last thing we get is our remainder. So our remainder would be 0, which proves that 2 is in fact a root. We also have just figured out if we were to do x to the fourth minus 16, 0x squared plus 0x minus 16, and do long division on x minus 2, it's always x minus the guy you're considering. Here are the coefficients we would get, starting with the degree 1 less. So instead of starting over top of here, we always move over 1. So we would get x cubed plus 2x squared plus 4x plus 8, and then plus 0, which we don't need to write because it's 0. Okay, that's a good place to stop.